Welcome to Maths with EJD. On our series of videos on integration, our attention is moved to a very important part of integration, which is integration by parts. Integration by parts. Interestingly, this has a little bit of connection with what we saw as product rule under differentiation. And this is an emphasis again that you cannot really do well with integration if you have not mastered differentiation. So you see, in the process of integrating, you keep having to differentiate. So integration by parts, occasions arise when we have to integrate the product of two functions like that, and all the techniques we have learned so far may not be applicable. So whenever you have to integrate two parts, in the case of differentiation, right, if you have to differentiate two parts, two or more parts, you needed to use the product rule. But if you have to integrate the product of two functions, in such cases, we can integrate by parts, as we will soon find out. Okay. So the formula for integration by parts arises from the product rule technique in differential calculus as follows. So of course, differentiation is also known as differential calculus. Integration is known as integral calculus. And I told you differentiation is like tearing things apart, removing things, separating things, while integration is bringing things up together, gathering things together, summing things up, basically. Okay, so as a refresher, you remember that in differentiation or differential calculus, we're talking about product rule, y was seen as u times v. U is a function of the same of x and v, and u is a function of x, and v is also a function of x. So you have y equals that. So y, where is y of x, u is u of x, and v. Oh, okay, v is missing here. So v is v of x. So and we saw there that dy dx, which is the product rule, is u times dv dx plus v times du dx. Now let's see how that applies to what we have to do here. So from what you have here, right, you have dy dx equals u dv dx plus v du dx. Imagine that you multiply through by dx, okay? Dx cancels this, dx also cancels this. And that is what we get in the next place, where we multiply through by dx, and we have dy equals u dv plus v du. And now we apply the integral. So you have integral of dy, just apply the integral. Integral of dy equals integral of u dv plus integral of v du. And of course, like I told you, integral of d something is something. Integral of the boy is boy. Integral of the q is q. So integral of dy is y, right? So then you have this integral of u dv plus integral of v du. So don't forget again that y is uv from where we started from. Y is actually uv. So you bring that back. So y is uv. And so you now have uv equals integral of u dv plus integral of v du. So from here, we now make, you could make either one your subject of formula, but we choose this integral of u dv. So integral of u dv now is equal to uv minus integral of v du. And that is what you have as your equation 18. So this now becomes the formula for integration by parts. And the thing about integration by parts is you keep doing this integration by parts until you have a chunk that you can integrate at once. Okay. So you may have to, depending on the kind of question you have, you need to keep going. And the key thing to do here is whenever, of course, this is arising because you have to multiply two functions, a particular function and another one. But then, so you have to be able to identify which of the functions. So let me see. Okay, let's just go. I think I'm jumping ahead of myself. Let's see. So that equation 18 now, which is integral of u dv minus uv, integral of u dv equals uv minus integral of v du, is the required formula for the integration of functions by parts. So to integrate by parts, you have to identify a part of the function u. So you need to identify a function u, which should be more easily differentiable. So your u should be something that you can differentiate, because you can see from here that you need du. So it means if you identify your u, it should be something you can easily differentiate to get du, while your dv should be something you can easily integrate to get v, because you need to integrate dv to get v. So in identifying which is which, make sure your u is something you can easily differentiate and your dv is something you can easily integrate. So something you can u easily differentiated to du and dv easily integrated to v, because those are the things you need in this part. You need u, which is normal u here. You need v, which you get by integrating this. You need v, which you get by integrating dv, right? And you need du, which you get by differentiating u. V you get by integrating dv. Okay. All right. So to integrate by parts, we have to identify a part of the function u, a part of the function called u, which should be more easily differentiable and probably goes to a constant after a degree of differentiation. So there's no guarantee that if you keep differentiating to end up getting to 0 one day, but if it can get to 0, all the better. So then the second part, dv, should be integrable, right? This dv part should be something you can easily integrate. Okay, so after identifying u and dv and obtaining, so from u you obtain du, from dv, from u you differentiate to get du, from dv you integrate to get v. So we can now substitute using the formula and integrate as appropriate. The process continues until part integration is no longer necessary. So how do you know part integration is no longer necessary? When you get to an integral that you can evaluate directly without having to break it down in parts. So let's see examples. Okay, I mean, if you have this expression now to evaluate I equals integral of x squared sine x dx, okay? In order to evaluate I now, which is integral of x squared sine x dx, so naturally, anything that will go to a constant one day, you know, you have x squared. If you differentiate x squared, you get 2x. If you differentiate 2x, you get x, you get 2. If you integrate 2, I mean, differentiate, did I say integrate since differentiate? If you differentiate x squared, you get 2x. If you differentiate 2x, you get 2. If you differentiate 2, you get 0. So that's a good sign already that x squared should be your u. So you take u to be x squared, and automatically sine x dx will be your du. All right? So that's how to make the choice. Now you're going to see trickier cases where you don't know which one to pick because the two of them do not go to constant. But of course, when we get there to, you know, you get the trick. So if u is x squared, you know du dx will be 2x, meaning that du will be 2x dx. And then if dv is sine x dx, it simply means that v, when you integrate dv, you get v. When you integrate sine x, you get minus cos x plus c, like we already saw under integration of trigonometric functions. So the secret here lies in identifying the correct u, knowing that u is x squared, and then getting the u to be this, knowing that dv is this, and knowing dv is sine x dx, and knowing that when you integrate dv, you get v, and when you integrate sine x, you get minus cos x plus c. So now that that is settled, then you can now go back to your I, which is uv minus integral of v du. So u is x squared, v, as you can see, is minus cos x. You can leave out the constant c because that can always come up after you're done with the whole thing. Then minus integral of v. So v here is minus cos x as you have it. And du is 2x dx. You can see du is 2x dx. So you just need to tidy up things now. So you have minus x squared. I mean, x squared times minus cos x. That's minus x squared cos x. Then these two, you can bring that out. This is x here. So you have x cos x dx. So this is still a product of x and cos x. So we cannot integrate this one directly. So we have to go again. But for us to be able to do that easily, so we just say this is minus x squared cos x plus 2, and we call this whole thing I1 because we cannot integrate this one directly. When you get to a point where you can integrate this directly, then you know you are done. All right. So here we call this 2I1, meaning that this expression is I1, and then we go again, repeating the same process. But don't forget, you are still going to come back to this place. Okay. So we go for that. So see that here, process goes on. You have sine I1. I mean, since I1 is integral of x cos x dx, cannot be integrated directly, we repeat the process by taking again. Of course, we've taken, we know when we differentiate x, it can go to a constant easily. So you say u equals x. So that means du dx will just be 1, you know. Du dx, you know, u equals x, right? So du dx is equal to 1. So if you cross multiply, it means that du is simply dx. That's why you have this. And then automatically your dv is cos x dx. All right, cos x dx. So when you integrate dv, you get v. When you integrate cos x dx, you get sine x plus c. All right. So now that you have broken that down again, you go back and say that your I1 is uv minus integral of v du. So what is u? U is simply x. What is v? V is sine x, as you have here, minus, what is v again? V is sine x. Then what is du? Du is dx. That's a good sign. Du is simply dx. And then you have x sine, you have I1 equals x sine x minus integral of sine x dx. So this is x sine x here. Then if you, now interestingly, you can directly integrate this. So if you integrate sine x dx, you get minus cos x plus that c, right? And then you have x sine x minus cos x plus c. Minus and minus is plus, so you have x sine x plus cos x plus c. So you have I1 totally integrated. So it means that you don't have to keep repeating that step. Now, so depending on the kind of question you have, you may have to do the process like 5 or 6 times before you get to that final place where you can integrate directly. But now we just did it twice and we are there. So, but don't forget, I1 is not what you need. What you need is actually I. So you have to go back to the previous I, right? Okay, I mean, it's somewhere far off. So the previous I had minus x squared cos x plus 2i. But this I now is x sine x plus cos x plus c. All right? So we have minus x cos x plus, you can expand this. So you have 2x sine x plus 2 cos x plus 2c. Now, c is a constant, right? So 2 times c is also still another constant. So you have minus x squared cos x plus 2x sine x plus 2 cos x. Then 2c, you can just call it d, which is another constant. So where d equals 2c is the arbitrary constant. And that is the end of that, all right? So you have to keep going until you can finally integrate like that. So that's the way to go. So once you see x raised to power something, that is a very easy decision to call it u. But then what do you do in a case like this? Look at this example 2. You want to evaluate I equals integral of e raised to power 2x cos x dx. Which should be your u? Which one should be your v, your dv? It's a very difficult choice to make, right? Because if you differentiate e raised to power 2x 1,000,000 times, you keep getting something with e raised to power 2x. If you differentiate cos x 1,000,000 times, you keep getting sine and cosine and cos. But how do you go? So maybe what you just need to do here is to just pick anyone as u and pick anyone as dv, because one you can capitalize on the fact that cos x will keep changing, cos and sine will keep changing, so you can easily get back to a point where you still have cos and then you can substitute. So let's see how that goes. So if you consider this now, it is not very clear the choices of u and dv to make, but we can make a try with, say, u equals e raised to power 2x and du is 2 e raised to power 2x. Of course, when u is e raised to power 2x now. So to differentiate this now, when to differentiate an exponential function like we did before now, you have y equals, say, e raised to power f of x, So your dy dx will simply be differentiate f of x, that's f prime of x, then multiply by the original thing, e raised to power f of x. So that means differentiate 2x, you get 2, and put it by the original e raised to power 2x. That's how you have du to be 2 e raised to power 2x dx, all right? And then dv is automatically cos x dx. That means v is sine x plus c, because when you integrate cos x, you get sine x. So here you have I to be uv minus integral of v du. So what u is e raised to power 2x, v is sine x, minus v again is sine x, times du. Du is 2 e raised to power 2x dx, all right? And then you have e raised to power 2x sine x minus 2 is out here. So you have e raised to power 2x sine x dx. So you have e raised to power 2x. Now, you see, this cannot be integrated directly, so we just say 2i1, okay? Because we still have to make that decision. Okay, so you call it 2i1, right? So don't forget where we are coming from. We want to evaluate I equals integral of e raised to power 2x cos x dx. But what we have here is e raised to power 2x sine x dx. So then we keep going. So for I1 now, you have integral e raised to power 2x sine x dx. So we can take again u to be e raised to power 2x. I think it's better to, if you took e raised to power 2x as u, keep taking it as u. Don't change so that you don't get in a maze you cannot get out of, So we take u to be e raised to power 2x, and that means du dx again is the same, 2 e raised to power 2x dx. You see, as you keep differentiating, nothing changes. Everything, it keeps remaining the same. And then your dv now is sine x. That means that your v is minus cos x plus c. So again, I1 is uv minus integral of v du. So u, again, is e raised to power 2x. Now, v is minus cos x. Forget about the c because you will take care of that by the time you're able to integrate directly. So you have e raised to power 2x into minus cos x minus integral of v again is minus cos x. Then dx is, where's dx? Okay, du dx. Okay, sorry, du is 2 e raised to power 2x dx, all right? So this is e raised to power minus So minus comes out here, e raised to power 2x cos x, plus this 2, you bring it out because it's constant. Then you have e raised to power 2x here, and you have cos x. So the minus also goes out, minus and minus. That's why you have this plus right here. Okay, so some tidying up there. So you see now that even this cannot be integrated directly, but if you remember where we're coming from, the problem we started with was e raised to power 2x cos x dx. And this whole expression was called I, right? So it means we have come back to the same thing we started with. And that can be a good sign sometimes. So since you're back at the place you started from, okay? So this thing now is exactly the problem you started with. So you can just simply call it 2i, you know? This is now 2i. This is the I you started with. So remember, I1 now is e minus 2x cos x plus 2i. So what do? Since you already have an I, remember what you had here. This is I equals e raised to power 2x sin x minus 2i1. So now your I1 is e raised to power 2x cos x plus 2i. So now see the loop looks infinite, but fortunately, we can capitalize on the fact that I now is e raised to power 2x cos x dx, which appears here is the same problem you started with. So what you do now is you put back this I1 with this new I into this place. So, and let's see how that goes. So now the other I was e raised to power 2. So we substitute 23 into 22 and obtain the result as follows. I is e raised to power 2x sin x minus 2i. So interestingly, this new I1 minus 2i1, right? So you have e raised to power 2x sin x minus 2i1. That I1 is minus 2x cos x plus 2i from where we are coming from, you know. I1 is minus 2x cos x plus 2i1. So you substitute that for I1, then you can now add your plus c now, you know. Now, so you have e raised to power 2x plus minus and minus is plus 2 e raised to power 2x cos x minus times plus is minus 2 times 2i, that's 4i plus c. Okay. So what do we do here? You have so this is 4i, right? So you have I is e raised to power 2x sin x plus 2 e raised to power 2x cos x minus 4i plus c. So you can collect the i's together. So you have I plus 4i equals e raised to power 2x plus 2 e raised to power 2x cos x plus this c, the constant of arbitrary constant. So now I plus 4i is 5i, and this is equal to e raised to power 2x sin x plus 2e raised to power plus 2e raised to power 2x cos x plus c. So you can divide through by 5, right? So you have 1 over 5 e raised to power 2x sin x. Then there was 2 here. So you have 2 over 5 e raised to power 2x cos x and 1 over 5 of c. 1 over 5 of c is a constant still. So you can just call that d. So what is your I now? 1 over 5 e raised to power 2x sin x plus 2 over 5 e raised to power 2x cos x. So though it looks like the thing could have continued forever, but since once you end up getting the question you started with, just call it the original name I and then put that together, and then you get this your nice expression, and that's so with that you get out of the maze. Okay, all right, so let's do the last question under this. We want to evaluate I, which is arctan of x dx. Arctan of x dx. Now the interesting thing is that it is a bit tricky to evaluate arctan of x dx, right? Since it is difficult to integrate arctan of x. So in this case now, you know already that it is difficult to integrate arctan of x. So can you just take it as u, where u is now arctan of x, and then if you differentiate that, if you already have dealt with, okay, well, I mean, we can quickly even do this. So you have u equals arctan of x. Like I told you already, this is inverse of tan, not reciprocal. Arctan is different from 1 over tan. 1 over tan is cot, but this is arctan or inverse tan. So, and the way to get rid of arctan is to take the tan of both sides. So you have tan u equals tan arctan of u. This cancels out. So you have tan u equals x. All right. So here now you need du dx, but interestingly, the u is not on its own. So or let's do this. We can say d dx of tan u, d dx of tan u is equal to d dx of the x on the other side. So we differentiate both sides. But since this has tan u, right, you have to call it ddu, just like implicit differentiation. So you have ddu of tan u, then you have to balance that up with du dx, all right? Du dx, and that is equal to d dx of x is simply 1, all right? So if you differentiate tan u, we already know that's sec squared u du dx, and that is equal to 1, all right? So that du dx is equal to 1 over sec squared u, 1 over sec squared u. And what is sec squared u? We already know that tan u is equal to x. Tan u is equal to x. So if tan u is equal to x, we know that 1 over sec squared u is the same thing as 1 over 1 plus tan squared u. We already know that 1 plus tan squared is sec squared. So 1 plus tan squared u, and that is equal to 1 over, tan u already here is x. Tan u is x. So tan squared u is x squared. So we have 1 over 1 plus x squared. And that is why we have our du dx to be 1 over 1 plus x squared, meaning that du alone, if you multiply through by dx, so du alone will just be equal to 1 over 1 plus x squared dx. So if you differentiate tan squared, tan inverse x, that's what you get. So if u is arctan of x, du is 1 over 1 plus x squared dx. So, I mean, it looks a bit messy, but I mean, if you get down to it, it's pretty good to go. All right. So we have dv equals dx. Now, because we have taken u to be arctan of x, right? So automatically your dv will just be the dx that is remaining. So dv equals dx. So if you integrate dv, you get v. Integrate dx, you get x. So that means you just have v equals x plus c. V equals x plus c. So you can say I equals uv minus integral of integral of v du. And what is u? It took you to be arctan of x times v. V again is just x here. Then minus integral of v, which is again x, du now, which is 1 over 1 plus x squared dx. Now, we can tidy up. So x comes back. So you have x arctan of x minus this x times 1. So you have x over 1 plus x squared dx. And then you remember that this is looking like, so this part now is looking like that tan part where we have to say x is equal to tan x. That's for trigonometric substitution. So if we do that now, of course, this one remains x arctan of x minus half. So if you do the tan thing, you have integral of 2 tan x all over 1 plus, this is tan x. So that's 1 plus tan squared x, 1 plus tan squared x. Oh, okay. In fact, I'm going too far. It's not necessary. I don't have to worry about that. So this is x over 1 plus x squared. So remember, when you differentiate the denominator and you get the numerator, we had a rule for that, right? So when we differentiate 1 plus x squared, we get 2x, but this is x. And we already know how to do that. We can just multiply 1 by x, and 1 can be half times 2. So 2 times half is 1. So if you multiply this by 2 and put half outside, you balance that out. So you have half into integral of 2x all over 1 plus x squared dx. So now if you differentiate 1 plus x squared, you get 2x. So this gives you the idea of the derivative function ratio, like that. So in that case, what happens? If you differentiate the bottom and you get the top, then the integral is simply the logarithm, the natural logarithm, the ln of the bottom. So integral of 2x over 1 plus x squared dx is simply ln 1 plus x squared, because the derivative of 1 plus x squared is 2x. All right. So we have 1 equals x arctan x minus half ln 1 plus x squared plus c. And with that, we come to the end of this seemingly lengthy part of this integration thing, integration by parts. So you need to be very smart in being able to choose your so the idea is to integrate u dv. So you need to be smart in choosing what u should be and what dv should be, and that is equal to uv minus integral of v du. So you choose U, differentiate to get du, you choose dv, integrate to get v, like you need there. So thank you so much for listening. So watch out for the last video where I show you some formulas for general formulas for integration that will be very useful, and some practice questions you can try your hands on every aspect of integration. And if you have not subscribed, please do that. Press the notification bell so you can always get new videos that come. Thanks, and see you again.